Welcome back. In the first 2 weeks of part 3 of the Solar Energy MOOC program, we have discussed all components that are needed to construct a PV system. This week, we will provide you the tools to design your own PV system. But first, we need some tools to determine how much solar irradiance is incident on the PV modules in the system. In other words, we have to first introduce you to some important parameters that describe the solar irradiance. The learning objective of this video is to understand how to measure and how to use the following parameters like air mass, global, diffuse, direct irradiance, and equivalent sun hours. In this picture, the global horizontal irradiation is shown all over the world, or in other words, the energy falling on a flat horizontal surface of 1 square meter, where the energy is expressed in kilowatt hour. As we can see, in different parts of the world there is a quite large spread of the irradiation available on the surface. Obviously, the regions with the highest intensity are located between the tropics, while outside such belt the irradiation drops until approximately 1000 kilowatt hours per square meters in the very north of the map. The difference is not only in the amount of energy received during the year, but also in how it's distributed during the year. Indeed, the more you move away from the equator, the more is the gap of daily sun hours between summer and winter. This is known as the seasonal variation, and it plays a very important role in the design and the reliability of the PV system, in particular for the storage. So if you want to produce the same amount of energy from 2 PV systems, one in the Netherlands, where the irradiation is almost 1100 kilowatt hours per square meters, and one in Abu Dhabi, where we have almost 2200 kilowatt hours per square meters, then the number of PV modules in the Netherlands should be almost the double of the PV modules in Abu Dhabi to generate the same amount of electricity for a year. So it is very important to look into the environment in which the PV system will be installed. So let's start with the solar irradiance. Here we will give you basic information about our sun and its spectral irradiance as it arrives at Earth. Then we will split the global irradiance in main components and define the equivalent sun hour for a certain location on Earth. The core of our star, the sun, is so dense that the radiation cannot travel freely. It is continuously absorbed and re-emitted until it comes to the surface of the sun. That is called the photosphere. Here, part of the energy is released as spectral irradiance, forming the sun spectrum as discussed in the first part of this solar energy MOOC. The temperature of the sun's surface is about 6000 Kelvin, and it behaves quite perfectly as a black body at the same temperature. In this graph, you can see the spectral irradiance or spectral power density of a black body as function of the wavelength. This is the most common way of characterizing a light source expressed in watt per square meter at a particular wavelength. This electromagnetic wave travels from the sun through the outer space until it comes to our planet. Due to the Earth's atmosphere, this nicely shaped black body radiation translates in something wavy and noisy. Just outside the atmosphere of the Earth, spectrum keeps its regular shape in reference to the by the sun emitted spectrum, and this is what we call the AM0 depicted in red. Then we let the sunlight travel through the atmosphere. The spectrum of the global irradiance received on a flat horizontal surface shows several dips in the spectrum that can be related to the scattering and absorption by air molecules and small particles in the atmosphere. For example, the absorption bands related to molecular oxygen, water, and carbon dioxide in the atmosphere are here indicated. All these molecules contribute to the absorption of solar radiation at wavelengths above 1000 nanometers. Instead, the green curve is the direct AM1.5 spectrum. It is obtained from the global AM1.5 spectrum by considering only the light shining in the directional normal to the illuminated plane. The shape of this spectrum is very similar to the blue curve, but its intensity is sensibly lower in the visible part of the spectrum. Now I want to come back to the meaning of AM or air mass, which is a measure of the length of the light path through the atmosphere. The reference to calculate the air mass is when the sun is at its zenith. And here, as we already seen, we can identify two spectra. First, the AM0 obtained outside the atmosphere and the AM1 obtained on the Earth's surface. However, not always the sun is perpendicular to the location, and thus the light has to travel through the atmosphere for a longer path. So the air mass is given by the ratio of the actual path length of the sunlight through the atmosphere L divided by its minimal distance, which is obtained when the sun is perpendicular to the location L0. The air mass can also be expressed as 1 over the cosine of angle theta between the sun and the zenith. Here the air mass 1.5 is depicted, also called the standard reference spectrum, since it's used to characterize cells at lab and industrial level. It is obtained when the sun has an angle of about 48 degrees with the zenith. When the spectrum is integrated over a certain wavelength range, then we obtain the irradiance, which is the power density of the light per unit surface. Here G is the typical letter to indicate the irradiance, and you can come across several subscripts with different meaning, but as long as you see the G, it means that you have a unit which is watt per square meter. This equation illustrates the integral of the air mass 1.5 global spectral irradiations. When we consider the entire wavelength interval that goes from 250 nanometers to the infrared at around 3000 nanometers, then the outcome of this integral is 1000 watts per square meters, the standard test condition. Such number is used to evaluate the performance of the solar cells and modules in laboratories and industry, and as I mentioned, is referred to as the standard test conditions. Now we are going to see how to measure the irradiance. We need a hardware called pyranometer and another type of hardware called the pyrheliometer. Basically, they are electronic devices that count how many photons is received by the surface, and then it changes this information into a voltage signal that can be read by the software. The light is absorbed in a black coating and converted into heat, and the sensor based on the thermopile materials below the black coating converts the heat into a voltage. Here we define the global irradiance as the sum of the diffuse component and the direct component. Many times in literature you can also find this acronym, so the GHI, global horizontal irradiance, DHI, which is the diffuse horizontal irradiance, and DNI, the direct normal irradiance. Let's have a look in detail at these different components and how to measure them with a setup such as the one depicted on the left. The GHI is measured with the pyranometer over here, and it's called the global horizontal irradiance because the pyranometer has very large eyesight, so it can get the horizon and the whole hemisphere on top of it. Of course, this should be set as much as possible parallel to the ground where you will actually install the PV system. The pyranometer in the red box number 2 measures instead the diffuse horizontal irradiance. It has the same configuration of the previous one, but a shading this obstructs the direct irradiance. An embodiment of the shading structure is the black ball here on top. And then the DNI is measured with the pyrheliometer, highlighted in the red box number 3. It's mounted on a 2-axis mechanical stage that follows the sun any moment of the day, and it always points towards its direct component. The direct normal irradiance is thus obtained by shielding the pyranometer in a black tube. In order to obtain the direct component on a horizontal surface, we have to multiply the direct normal irradiance by the cosine of theta z, which is the angle between the zenith and the sun position. One last definition to discuss in this lecture is the equivalent sun hours, also called the peak sun hour. An equivalent sun hour specifically is an hour during which the intensity of the sunlight is 1000 watts per square meters. The equivalent sun hour is used to measure how much solar energy is available in an area during a typical day. In the graph we see the irradiance of the solar irradiations during one day. The area under the curve in yellow corresponds to the solar insolation, which is given in energy per unit area. In order to obtain the peak sun hour, the solar insolation has to be divided by the irradiance of the AM 1.5, which is 1000 watts per square meters, and the result is the number of hours. The corresponding graph of the irradiance has the rectangular shape that covers the same area of the other graph. In the last slide, the insolation in terms of annual average equivalent sun hours is shown expressed in equivalent sun hours per day. 5 regions can be distinguished and are highlighted with these different colors. For instance, in the Netherlands, the annual average equivalent sun hours per day is 2.7 hours. So depending on the position on the Earth and the position of the sun in the sky, terrestrial solar radiation varies both in intensity and the spectral distribution. In summary, the concept of air mass is introduced and the impact of the air mass on the solar spectra have been discussed as well. The global irradiance consists out of 2 components, the direct and the diffuse irradiance. Using pyranometers, it was shown how to measure the global, the diffuse and the direct irradiance outdoors. Finally, the concept of equivalent sun hours was introduced. In this video, we have defined the important concept that allows us to describe the solar irradiance. In the next video, we will discuss how much irradiance is incident on a PV solar module. So, see you in the next video.